This tutorial is going to discuss the different molecular shapes we worked on in class and discuss how to create those shapes from Lewis dot structures. So in front of you, you see the different names for the shapes that we discussed. We have linear shapes. In linear shapes, you notice that there is either one electron domain or two electron domains. We'll talk about what those electron domains really mean later on. Essentially, linear creates a straight line of molecule that is a straight line. Trigonal planar, you'll notice over here, is a flat shape that involves four different atoms or four atoms and they form to create what looks like a triangular shape that's flat. We have bent and angular. These green circles show the lone pairs, the ones that do not have atoms attached to it, and essentially you have three atoms that create a bend. In this one, this is our base structure. When we have four electron domains, it is called the tetrahedral. Again, these atoms are trying to be as far away from each other as possible because each of these atoms has a negative electron cloud that it's being repelled by. And then lastly, we have trigonal planar. Keep in mind, this is again a lone pair. It's not an atom that's attached to it. And it creates this sort of pyramid in a way, and that's why it's called trigonal planar. So let me work through the different types of shapes and how we get those from the Lewis structure. So to start off with, we have CF4. Now the first thing you need to do is you need to go to your periodic table, and looking at your periodic table, remember at the top of the column, or if you work through how many electrons carbon has, and knowing that you have 2 electrons in the inner shell, and from there on out 8 electrons. I know carbon has 6 electrons, so that means 2 are in the inner shell, 4 are in the outer shell, and so I know that the dot structure for carbon is going to have 4 dots. Alright, so we'll start off by more or less just listing what sort of dot structures each one is. Fluorine, I look at that one at the periodic table and it looks like it's going to have 7 valence electrons. And just a reminder, remember when you have just a single electron in one of these regions, that means there can be bonding here. So carbon is considered the universal atom, the one where so many different things can be built because it has 4 different locations where you can attach atoms to construct all sorts of things. Fluorine, on the other hand, has just one location where we can attach an atom and create a bond. Now these pairs that are electrons are called lone pairs. Because there are 2 of them, that is the max that can be held in what we call that orbital. And so they will not be bonding because they already have the 2 electrons that they're looking for. So in terms of Lewis dot structures, we can add those in there and create a combination. So I always like to start with carbon. The reason I'm starting with carbon is I know that there are 4 places where carbon can bond, and using a different colored pen, I'm going to now add the fluorine. So fluorine, if you remember correctly, has 7, and because I have 4 fluorines, each one of those fluorines can attach to one of the carbon electron domains. So let's double check, and this is absolutely key, that you have those 8 electrons that are expected in each orbital, because remember each atom wants to have 8 electrons to be stable. And so when you look at this, when you look at this, it looks like the carbon has its 8, so that works out fine for the carbon. We have fluorine that has its 8 on all sides, so it looks as if each of these atoms has fulfilled the octet rule, which is having 8 electrons in its valence shell. So now let's rewrite that as a structural formula. So in this case, we'll use red. We're going to, wherever you see these 2 dots, one from one atom and one from the other atom, we're going to create a dash. And so in this case, I have carbon. It looks like there's a bond, a covalent bond that happened here where they're sharing electrons. And put those lone pairs on there. And here we have our structural formula with the lone pairs. So what does that look like? Well, we know we have 4 electron domains, one here, one here, one here, one here, from that carbon. And so that requires those sticks that we had used toothpicks with to be as far apart from each other as possible. Here's the carbon. And so this shape here is a tetrahedral. And there you have it. So you actually have to label that tetrahedral. Yes, you do need to actually memorize these. So let's try another one. For the next one, we have SBr2. So for this one, I already set up the Lewis dot structure. Sulfur has 6 valence electrons, and bromine has 7, and I sort of had open circles for the bromine and the solid circles for the sulfur. And so in that case, it looks like sulfur had 2 locations, or 2 places where it could bond, and the bromine attached to both of those. So they share an electron in this region and then in this region. The key in all of this one is that when you look at sulfur over here, you again see you have 4 electron domains. You have one over here. This lone pair is considered an electron domain, another electron domain here, and one more here. We're going to ignore the electron domains over here because bromine isn't attached to anything else other than just the sulfur. So in that case, if we know that sulfur has 4 electron domains, that means that sulfur has 4 sticks, in other words, like we've been talking about, that are poking out of it. But in those regions, there are only 2 regions where you have an atom actually attached. And so when you look at this shape, you're going to see a shape that looks very similar to what we call being bent. Be certain to still include those electron domains, because if you didn't have those, instead you'd have something that's linear. But these electron domains force this to be a bent shape. Let's work through this one. So for this next molecule, we have phosphorus with 3 fluorides. Phosphorus, when I look at my periodic table, tells me that it has 5 valence electrons, 1, 2, 3, 4, 5. You notice that we have already a lone pair up here, but not a lone pair anywhere else. So that means that each of these single electrons is a location where a bond can happen, where they can share electrons. So fluorine will attach to those regions, and it has 7 valence electrons. And if we were to rewrite that as a structural formula, you'll see that you have then a shape, or better said, a structure that looks like this, where phosphorus has still 4 electron domains, one here, one here, one here, and one here. That means, again, phosphorus is in the center. We have the 4 sticks coming out of that. And in this case, though, we have 3 atoms attached to it, all 3 of those being fluorine. And here you do not have one, but because of this being still an electron domain from this lone pair, it forces these here to come down at an angle, because remember, all these electrons want to be as far away from each other. And this is considered a pyramid. All right, let's move on to the next one. This one here is a little bit unique because you have carbon having 4 electrons in its valence shell, and oxygen having 6. So if I do it this way, you'll see that, I'm going to put 1 oxygen on each side, that we have here a lone pair, here a single electron, here a single electron, here one, and here one by themselves. And so in that case, what is it that we can do for these single ones? And that is that this electron will actually move over here, and this electron will move over there to create what we call a double bond. And that's the case for this one as well. Keep in mind that the electrons have to come from different atoms, and it makes no difference from which region they come from the different atom, as long as it's one from oxygen and one from carbon. And so we have now something that is a double bond of oxygen and carbon, carbon and oxygen. There are no lone pairs here, so in this case we really just have 2 different structures being as far apart away from each other, these oxygens, all attached to the carbon. In this case, we would call that linear. So for this one here, let's take a look. Carbon has 4 valence electrons, and we're going to use oxygen next. Oxygen, try to do the hydrogens last. Oxygen, I know, has 6. And then it tells me I have 2 hydrogens, and I know each of those just have a single bond. And so 1 electron that allows that single bond. So I'm going to put electron here and 1 here. And it makes no difference if I put it here or anywhere else, as long as you have 1 on in each region around the carbon. So could I put it on the hydrogen, on the oxygen? The answer is I could have, but then I would have quickly noticed I have these 2 electrons that are single electrons that have no other atoms that they'll bond with. And so for that reason, this arrangement with having the hydrogens be both on carbon allows me to move this single electron and this single electron over to create a double bond, so that what I am actually seeing is a bond of hydrogen with a double bond of oxygen with a bond of hydrogen again. And in this case, you have now 3 electron domains. And because you have 3 electron domains, we consider this trigonal planar. And that's going to look very much like what we see right over here, this trigonal planar one. Nice and flat, but in a